Okay, so we have this data sufficiency geometry worksheet. So remember, all of you, that the worksheet can be accessed through the link given in the description of this video. Solve the worksheet first and then come to this video for the solutions. Let's begin. Find the area of the triangle BEF. That's this one. BEF, this triangle. Now, what is given to us is 5 centimeters length of AD, 3.5 centimeters length of DC. So that's the information we have. Now, triangle ABC is an isosceles triangle. So this triangle ABC is an isosceles triangle. ABC. This triangle is an isosceles triangle. And side AC is the diagonal of the rectangle ADCE. So there's a triangle and then there's a rectangle. So AC is the diagonal of the rectangle ADCE. Okay, fair enough. Now, can we find the area using the first statement? No, because we don't know whether FE is perpendicular or not perpendicular. We don't know the information about FE, right? It looks like they're parallel. Okay, now let's see. A, B, C, D, E. A doesn't help. D is out. Yeah. B. Side FE is parallel to side AC. So AC is parallel to FE. Okay. Right. But on its own, using the second statement, we can see that AC is the diagonal. We can see that this is a rectangle, 5 centimeters, 3.5 centimeters, correct? But we don't know that this ABC is an isosceles triangle. We don't know that, correct? And because of that, we cannot solve this question. So B is out. Now, when we take both the statements together, then we know that ABC is isosceles, right? And we know that FE is parallel to AC. Then using similarity, we can find out the area of this triangle. So the question is how? Let's solve it. So basically, you don't need to solve it. Once you figure out that you can get to the answer, then C is the answer. Together they'll help, but we'll do the calculation for the sake of understanding. Okay. So how does the similarity come in the picture? So look at this. If the triangle is isosceles, then this is 5 centimeters and this is also 5 centimeters because the AE is perpendicular. It's a rectangle, right? Yeah. And in an isosceles triangle, the perpendicular, right, will bisect the opposite side. This is only for an isosceles triangle into two equal parts. All right. All right. So now we know that triangle ABC, right, to the triangle BEF in question have corresponding sides, that is 10:5, correct? Which is 2:1. And if we square their corresponding sides, we get the ratio of the areas. So all we need to do is find out the area of the triangle ABC. So if the triangle ABC area is half base times height. So that's half, base is 10, and the height is 3.5. So it is 5 times 3.5, whatever that is, okay? 17.5, I believe. 5 into 0.5 is 2.5, and 5 is 15. So that is 17.5. And so the area of BEF is 1/4 of this, okay? Right? If this is 4 times, right, then 1/4 of it is this. All right. 1/4 of 17.5 will be the area of BEF. Whatever the case may be, we are able to find out the area of the triangle BEF using similarity property. Okay. Right. Moving on. Second question. Find the area of the green shaded sector GAC, right, where G is the center of the circle. Chord AB is equal to BC. Now, looking at the figure given over here, we already know that this is 60 degrees. Okay. Using the property that the arc AC subtends an angle at the center 120, then the arc AC will subtend the angle on the circumference, which is half of 120. So that's 60. So from the given figure, we know that this is 60 degrees. From the first statement, we come to know that the triangle formed ABC will be a will be an equilateral triangle because they're saying that AB is equal to BC. So if these two sides are equal, the angles opposite to them, yeah, will be equal as well. So it'll form, obviously this is 60, 120 remains, so 120 divided by 2, 60, 60. So it forms an equilateral triangle. However, even though if it's an equilateral triangle, right, we yet don't have the measurement of the radius, correct? So without the measurement of the radius, we cannot find out the, you know, the area of the green shaded sector, right? So A is not enough, D is out. Now area of the sector is found out by using the angle theta, which we know, upon 360 into 2 into pi r square, into pi r square. So therefore, we need to know the radius to get to the answer. Without the radius, we don't have the answer. Okay. B, the radius is 1 by root 3, the length of the chord AB. Now using that statement alone, yeah, we need to know the length of the chord AB, right? If the radius is 1 by root 3, the length of the chord AB, yeah, we yet don't have the length of the chord AB, yeah. So that way, we don't know, we don't have an answer using B as well. Using both statements together, so this is both statements together is length of the chord AB, okay, which becomes the side of the equilateral triangle. And again, whether it's a side or chord AB, we need the length of chord AB to get to the radius. So we don't have any measurement. So both together also is not answering. E is the answer. Okay. There is no measurement, so there'll be no way we can find out the green shaded sector. Okay. Anyway, moving on. Third one. Is the length of the diagonal of a parallelogram ABCD equal to 8 centimeters? So let's solve this. So let's say this is a parallelogram. Yeah. Okay. And it's ABCD. So the diagonal length is at 8 centimeters. Okay. So parallelogram ABCD has longer sides, 12 centimeters, and the shorter one, 5 centimeters. Okay. So it depends upon the angle, right? It depends upon the angle. So if we know the angle, then perhaps we could find out whether it's equal to 8 centimeters. As of now, it could be 8 centimeters, it could not be 8 centimeters. All right, is the length of the diagonal of the parallelogram. Now that they're not talking about both the diagonals, all right? If any one diagonal is 8 centimeters, we got an answer. But out here, using the first statement, we don't have the angle, at what angle the parallelogram is formed, right? So it could be 8, it could not be 8. So first statement doesn't answer. A is out, D is out. Now, second statement. When the sides of the parallelogram ABCD are perpendicular to each other, so now we know the angle is 90 degrees, the length of both the diagonals equal to 13 centimeters. So basically it's saying it's forming a right triangle, right? Okay. So we know the diagonals in a rectangle, yeah. I'm sorry, I must have said triangle, so that was a slip of tongue. That means it's forming a rectangle. So in a rectangle, you know, the diagonals are equal, correct? But yet we don't know the dimensions. We don't know the dimensions, correct? We don't know the dimensions. And it says when the sides of the parallelogram ABCD are perpendicular to each other. So the question is the length of the diagonal of the parallelogram ABCD equal to 8 centimeters? And here they are hypothesizing that if the sides of the parallelogram ABCD are perpendicular, so when they become perpendicular, yeah, the diagonals are equal to 13 centimeters. So that doesn't answer the question. So B is out. Taking both the statements together, yeah, all we know that 5 and 12 when becomes perpendicular, then the diagonal obviously will be 13 because it's a right angle triangle Pythagoras theorem property, correct? So that's fair enough. Okay, all right. But even when we take both together, the second one is hypothesizing it that okay, 5 12 when it becomes perpendicular, it's 13. So okay, makes sense. 5 12 13. Yeah, but is the length of the diagonal of the parallelogram ABCD equal to 8 centimeters? Do we have a definite answer? Again, no, right? All we know, yeah, that from the first statement we know that the diagonals, correct, has to be lesser than the sum. So if this is a triangle that we are looking at within the parallelogram with dimensions 5 and 12, then we know that the third side, the unknown side, yeah, which is the diagonal, has to be less than the sum and has to be greater than the difference. So that rule we know, correct? That rule we know. And with that rule, we know that it could be 8, it could not be 8 also. We don't know. Using both statements together, they are just confusing us. It's not answering. E is the answer. All right. E is the answer. Okay, moving on to the fourth one. Find the ratio of the side length of the smallest square, yeah, that one, to the side length of the largest square ABCD drawn below. So this is the largest square ABCD. So they want to know the ratio of the sides basically. So basically you could say this side, I'll mark it in red, this side to the big side AB. They want to know the ratio of these two. Okay. Smaller one to the bigger one. Okay, first statement A, B, C, D, E. Yeah. Each square drawn inside square ABCD are drawn such that the vertices of the inner square touch the midpoint of the side lengths of the outer square. So now we know how are these inner squares drawn. Like we know that it is touching the midpoint of the outer square side. All right, all of these. And so that's how it goes. So using A alone, we get the answer. All right, A alone, we get the answer. How? All right. So let's assume that the outer side is X. All right. So even this is X because it's a square they're talking about. Yeah. So even this is X. Now if that is X, then this X is the diagonal of the inner square. Diagonal of the inner square. Yeah. So that is X, diagonal of the inner square, right? Right. Now, if the diagonal of the inner square, where it's a square, so all are 90 degrees. So this is forming a right isosceles triangle. Right isosceles triangle. This half. I'll just shade it as blue. So this blue portion is a right isosceles triangle. Okay. Yeah. So in that case, this would be x by root 2 and x by root 2 using Pythagoras theorem. Okay. So that now we know that x by root 2, yeah, upon x and that will be the series throughout. Smallest one to the next bigger one will be x by root, and then this one to the next bigger one will be, x by root 2 upon x. So basically, let's find out. So the ratio is 1 by root 2. X and x cancels. The root 2 comes down. So we know that the immediate smaller square to the immediate larger square, yeah, is in the ratio of 1 is to root 2. And they're asking, find the ratio of the side length of the smallest square to the side length of the largest square. And so we can figure it out. Without using any dimensions, we can figure it out. So let's go one step ahead. So I know this is x. I know this is x by root 2. So now we'll figure out that if this is x by root 2, now we'll figure out the third square, right? We figure out the third square. So in the third square, yeah, the diagonal length, yeah. So I'll just clean all the drawings, yeah. So this we know is x. This we know is x by root 2, yeah. And this side is the diagonal of the third square. So again, when we look at the third square, if this is x by root 2, then these two sides out here, because of the right isosceles triangle, they are equal, right? Okay, so it'll be x by root 2 and divide by root 2, which is nothing but x by 2. X by 2, right? So now we know that this side is basically x by 2. And so on, we can figure it out. Okay, so it's something like that. First square, second square side is x by root 2, third square is x by 2, fourth square is x by 2 root 2, so that root 2 keeps coming in. And then we have this fourth square, this is the fourth square, and the fifth square. So there are five squares, 1, 2, 3, 4, and 5. So there are five squares, right? Yeah, so there are five squares. So this is x by root 2, this is x by 2, this is x by 2 root 2, and then final one will be x by 4. 2 root 2 root 2 is 4, right? So the smallest side length of the smallest square is x by 4, and the largest one is x. So literally, we did not require any dimension. The ratio is 1 is to 4. Got it? So A answers. A answers. So B, C, E is out. Now, second one, area of the innermost square is 4 square centimeters. Okay, now this is a tricky one, right? If the area of the innermost square is 4 square centimeters, remember one thing, that we do not know how the inner squares are drawn. Like in the first statement, they've clearly stated that the inner squares are drawn by having their vertices at the midpoint of the outer square, and that's how the squares go. But with the second information, okay, so the inner square is 4 square centimeters, yeah, area of the inner square, but we don't know whether these are the midpoints, the vertices are touching the midpoints. It could be something like this, where it could be a square, yeah, but not necessarily touching the midpoint, yeah, or it could be a square, yeah, and we can see it's touching, but uh, it could very well be the case that it could go out and in like that, we don't know, right? Or it could be something like that, we don't know. Okay, so the second statement alone doesn't give us an answer. We know that find the ratio of the side length of the smallest square to the side length of the largest square ABCD drawn below. Now, we know that the smallest one is a square, largest one is a square. So we don't know whether the second, third, and the fourth one are actually squares or rectangles. We don't know we don't have information to that. Correct? Right? So the second statement on its own is not helping. Correct? So therefore, second one is not answering, only A is answering. Okay? Yeah. So we cannot assume that, uh, you know, all of these are squares from the second statement alone. But with the first statement, each square drawn inside square ABCD are drawn such that the vertices of the inner square touch the midpoint of the side lengths of the outer square. So each square drawn inside square ABCD. So we know that all of them are squares. Okay. Anyway, So that's one argument, that we don't know whether they are squares, and the second argument is whether they are touching the midpoints or not, right? Yeah. All right. So I think I think that even if it was just touching the boundaries of the outer square, and we knew that they were all squares, then probably the answer would have been, we could have got to the answer. We could have got to the answer. So that midpoint property is not a property that we can use, because we can get to the answer whether or not it is the midpoint. Okay, as long as it's touching and we know that they're all squares, we get the answer. But with the second statement, we don't know for a fact whether the second, third, and fourth are squares. So that's the argument for choosing A as the answer and not B. Okay. Yeah. All right. Moving on. Fifth question. For the polygon given below, what is the measure of the angle marked X? First statement. So first of all, we know it's a hexagon. Yeah. All right. Now, the point where the blue lines meet is the center of the given polygon. Okay, so we know that this point out here in green, yeah, is the center of the polygon, right? Now, we know that it's the center of the polygon, but we don't know whether this polygon is a regular polygon, meaning it's a regular hexagon or no. We don't know that. Had it been a regular polygon, equal sides and equal angles, then we could say that X is equal to what? Yeah. But the first statement only tells us that the where the blue lines meet is a center. So what I'm trying to tell you is that it could be something like this, right? Yeah. It could be something like this. And if it was something like this, and this is what is happening. So this angle versus this angle, you can clearly see the difference. Are you with me? Yeah. All right. Okay. So we wouldn't know exactly what the X would be with the first statement. So A is out. Yeah. D is out. Second statement, the given polygon has all sides equal and all angles equal. Fair enough. So the second statement tells me that this particular polygon is a regular polygon, but it does not tell me whether this is the center or not. So it could very well be that this is my regular polygon. Yeah. But the X formed is not in this is the center, but X could be out here. They're asking this angle. Are you with me? Not touching the center. So from the second statement, we don't know whether the X is formed at the center or not the center, because that can change the answer. If it's at the center, we know the answer. But we don't know for a fact whether X is at the center or not. So that we don't know. So from the statement, yeah, in the question, what is the measure of the angle marked X? In the question itself, it doesn't tell us whether the X is at the center or not. So it's only the first statement that's telling us that. So B is out. Taking both together, we get to the answer. When we take both together, we know that the X is formed at the center and the regular hexagon, and it's a regular hexagon, meaning all sides are equal. So once we know that, then it becomes quite easy to solve the question, because we can simply draw the diagonals. Yeah. And when we draw the diagonals, we come to know that a regular hexagon forms six equilateral triangles, the way you see out here. And we know that this is 60, 60, 60, 60, 60, and 60. And this angle is clearly asking you, yeah, these ones, 1, 2, 3, and 4. So that's 64, that 240. So we can know that X is 240 degrees when we take both the statements together. Yeah. Okay. Question 6. A solid cube with side length 5 centimeters is painted red on all its surfaces. The cube is then broken down into identical small cubes. Find the probability that a small cube picked at random has no surface with red paint. Okay. Now, we don't know that this 5 centimeter cube is broken down into identical small cubes of what size. All right. Yeah. So, therefore, we cannot really answer this question. Yes. So, we look at the first statement. The total number of small cubes formed is 125, and the sum of the volumes of all the small cubes is equal to the volume of the solid cube with side length 5 centimeters. So the big solid cube of side length 5 has a volume of 125 centimeter cube. And this 125 centimeter cube, using the first statement, tells us that it is forming 125 identical smaller cubes, right? It uses the word identical, very important information. Without that, we couldn't have answered this question also using statement one. Yeah. And the reason behind that is very simple, that if they're not using the word identical, then the broken down part, yeah, uh, you know, doesn't tell us whether these 125 are of the same dimension. Okay. So there could be 125, but one could be smaller, one could be bigger, and therefore find the probability that a small cube picked at random has no surface with red paint. It could not have been answered. Yeah, if the word identical is not there. But then see, let's not hypothesize. Let's go with the question. The question states identical. Now, the first statement clearly tells us there are 125 smaller cubes formed, and the sum of their volumes is equal to the volume so of the bigger cube. So we can simply divide the volume of the bigger cube with the total number of cubes, which is 125, and that gives me 1 centimeter cube for the volume of the smaller cube, right? And if the volume of the smaller cube is 1 cc, that means we know that the side length of the smaller cube is 1 centimeter. Yeah. And so now we know that if the side length is 1 centimeter, that means we are forming uh, identical smaller cubes of the side length 1 centimeter. Then we know that there are exactly 27 cubes which are hidden. Yeah. Which are hidden from the view. Like if you holding a a cube in your hand, yeah, then imagine that there are these 27 cubes which are hidden inside inside the cube, which are not visible to the eye. And so when the big cube was painted red, yeah, only the outer surfaces, right, only the outer surfaces got the red paint on it. Okay, so this is the first surface, right? And then there's a second one which is inside. So from the top view, I can show it to you that this is your, 9 things hidden. So the top view shows you 9, but that 9 is starting from the second layer. So this is my top layer, right? Then this is my second layer, third layer, fourth layer. So the fifth layer is painted red. The fifth layer is painted red. So it is the hidden portion inside. So difficult to imagine, and that's why this question becomes difficult. So we know that there are 27 cubes right in the center. So imagine it's a like you have your Rubik's cube. Rubik's cube has 9 tiny cubes, right? If I'm not wrong, or probably 5. I don't know. I don't remember. Yeah, I think it's 9. So imagine the Rubik's cube is covered with another layer of of surface which has 5 cubes from all the sides, and that's what it's like. So when the Rubik's cube is found inside, yeah, and the outer layer is covered with a layer of 5. So let me see if I can draw it for you and show it to you. Yeah. Maybe if I can draw a good diagram, then perhaps you can view it. Yeah. So let me try and draw it for you. Hang on. Okay. Yeah. Okay. So again, I hope you can see this. And this is my, I'll draw it in red. Okay. 2, 3, 4, and 5. This is 1, 2, 3, 4, and 5. Yeah. Okay. 1, 2, 3, 4, and 5. Okay. And then you have 1, 2, 3, 4, and 5. 1, 2, 3, 4, and 5. So what I'm trying to get to is basically, hmm, it does get confusing, but I'll keep up. Yeah. What I'm trying to get to is, maybe I'll use freehand. Hang on. Okay. So now focus on this red portion, right? Yeah. There are 9 cubes that you can see. Okay. And now if I would eliminate the blue portion entirely, because these are all visible, right? This blue portion is all visible, correct? This entire blue portion I'm removing, all the outer layers. Now, if I peel off the outer layers, including the top layer, then you'll see that this portion, yeah, this 9 out here inside, yes, would be showing you 27 cubes which are not painted red at all. So using the first statement, you can get to the answer that if I pick one of these 125 cubes at random, then I know that the probability that I pick a cube which has no surface with red paint on it is 27, because these 27 are the hidden layers inside, are the 27 cubes formed inside which are not painted red at all. It's a hidden cube. So my answer would be 27 by 125. So A gives me the answer. A gives me the answer. So therefore, A and D is what we have left with. Now, second statement. If the solid cube with side length 5 centimeters is broken down into 2 centimeter side length small cubes, then all small cubes will have at least one surface painted red on it. So let's go back on this same drawing out here. Yeah. So in the same drawing, now instead of focusing on the red one, which I've already drawn, let me redraw it for you. Okay. Let me use green color to show you 2 centimeter side length. Okay. So this is my green color, 2 centimeter side length. Imagine this is 1 centimeter each, right? So I have 1 2, right? Correct. And then I have 1 2 out here, correct. And so from the side view, okay, I'm utilizing 8 total cubes. So maybe I can show it to you out here. Let me get rid of the last layer out here. So I'm getting rid of the last layer, that one, okay, that one. So what I'm utilizing is these four, which includes this and this. Yeah, this is my 1 2 2 centimeters, and then I have another two out here. All right, correct. And these two will carry on to this layer and this layer. So again, let me draw a neat diagram. Yeah. So if this is 5 centimeters in length, then this is what I'm talking about. This is 2 and 2 and 1, 2 and 2 and 1. So what I'm essentially talking about is 2 and 2, 2 and 2. So I'm essentially forming, yeah, 8 cubes, 4 on the top and 4 at the bottom, right? And they all are painted red on the outside. So then all small cubes will have at least one surface with red paint on it, but it's not really answering the question out here. Find the probability that a small cube picked at random has no surface with red paint. Now, this small cube could be these 125 or these 8 out here. These are the 8 cubes formed and these are the 125, correct? So it could be this situation or this situation from the second statement. Are you getting it? Right? Just because if the solid cube this thing, if the solid cube with side length 5 is broken down into identical 2 centimeter side length cubes, right? So from the second statement, they're hypothesizing again that if that 5 centimeter was broken into 2 centimeter small cubes, then then all small cubes will have at least one surface with red paint on it, but it's not really answering the question, right? Yeah, it's not telling us that it's broken. It's saying if this would have happened, correct? So if that could have happened, then this could have also happened, right? If we look at the second statement, and hence we get different answers. All right. So B statement is not answering the question, and hence A is the answer. So using the first one, we got the answer. Yeah. So A and D was out. So now B is not answering. Therefore, D is out. So only A answers the question. Right. Question number 7. So another tough one. So those who have no problem imagining volumes, then for them these could be easier questions, and those obviously would practice a lot. So water tank made of transparent glass has height of 40 centimeters. Yeah. Okay. So that's my water tank, and 80 centimeters length and width of 40 centimeters. So that's my height, that's my width, and that's my length. Okay. And has water up to the height of has water up to the height of 10 centimeters. I'm going to use a blue color for the water. So this is my 10 centimeter line. Yeah. So that much is the water in it. Yeah. Okay. Up to 10 centimeters. If a solid cube is placed in it such that it completely submerges in the water, then what is the increase in the height of the water in the tank? All right. So a little bit of physics out here. So whenever a solid, a solid object is completely immersed, right? Then that solid is now occupying the space of what originally was water. All right. So so obviously, if the solid is completely submerged where there was originally water, then it's occupying the space of the water. And that water now needs to get displaced somewhere. So where does it displace? The water gets evenly spread out in the length of 80 and the width of 40. Yeah. And it would increase by that much volume which is displaced by a tiny amount. It would increase by this tiny amount because you can't simply say that I put something in the water, displace the water, and the water doesn't go anywhere. It goes inside the fish tank only. The height increases. Okay. So it displaces by the volume of the solid which is placed in it. So all we have to figure out is if you know the volume of the solid cube, the small cube which is placed in it in the fish tank, then we can get the increase in the height of the water tank. Yeah. Now statement A. The length of the body diagonal of the solid cube is 4 root 3. So this particular solid cube, yeah, its body diagonal, yeah, that is the body diagonals from here to here, yes, is 4 root 3. Now remember that body diagonal of a cube or any rectangular solid, yeah, is length square, width square, sorry, into height plus the height square. Now for a cube, the length, width, and height are all the same. So it is 3 times L square, which is root 3 times L or the side, right? Or the side. It could be the length or the side. So this L is nothing but 4. So we know that the length of the cube is 4. Therefore, we know that the volume is L cube, which is 4 cube, which is 64 centimeter cube. Yeah, 64 centimeter cube. And that 64 centimeter cube is getting displaced where it is getting displaced in this fish tank where the width is 40 and the length is 80 and the increment of the height is h, and that h is what they're asking, what is the increase in the height. So it is 64 over 40 into 80. That's my height. So this 64 is 8 tens are 8 eights are 8 goes into 45 times. So it's increasing by 1 by 50, which is 0.02, because 1/5 is zero point 0.2 divided by 10, 0.02. So we know that from the first statement, we get the answer. So BCE is out. So it's either A or D. All right. Okay. Now the second statement says the volume of the solid cube, yeah, that is this small cube, is 1 by 2000 times the volume of the water tank. So what is the volume of the water tank? Length into width into height. 0, 0, 0 goes with these three zeros. 2 goes into 8 4 times. So we got 4, 4, and 4. That is 64. So we come back to the same volume that we got before from here. So even the second one answers the question. We come to know the increment in the height using the same understanding. So A answers, B answers, therefore each alone answers. So seventh one, the answer is D. Now remember, these data sufficiency worksheets are meant for advanced learners. So that's the reason those who have not practiced enough or uh, you know have average understanding of math, they'll find these worksheets difficult or my solutions difficult to follow. Yeah. Question 8. Does a right circular cone have the same volume as a hemisphere. All right. So remember, hemisphere is half of a sphere. So basically, if you have a ball-shaped sphere, yeah. So basically a ball, yeah, and you cut it into half, it forms a hemisphere. And right circular cone, it just means an upright. So that word right means an upright cone. Otherwise, you'll have cones like this, right? Diagonal. But you have an upright cone where the tip is coinciding with the center of the base. Anyway, yeah. So moving to the question, does the right circular cone have the same volume as a hemisphere? So now, remember, volume of the hemisphere is 4 by 3 pi r cube. Yeah, that is for the sphere. So the hemisphere will be half of this. Therefore, the hemisphere will be 2/3 pi r cube. This is for the hemisphere. And for a cone, it is 1/3 pi r square h. First statement, the right circular cone has a circular base identical to the hemisphere circular base. So all they're saying is that if this is my right circular cone, yeah, then this base is identical to the hemisphere, right? So remember, if the bases are the same, but we don't know about the height, correct? We don't know about the height. So we know that the volumes could be equal or could not be equal from the first statement, right? It could be equal, could not be equal. So this cone could have the same volume as this hemisphere, right? It could also be drawn this way, where this is my hemisphere, yeah, and this is my cone. In that case, clearly we can see the hemisphere has a greater volume than the cone out there. So it could be yes and no situation. We don't know. So A doesn't answer, D doesn't answer. So we're left with BCE. Second statement, the right circular cone has a height identical to that of the hemisphere. So this time the height is the same. So it could be a situation now, something like this. So remember, this is for A. For the B, the situation could be like this. So we have a cone and we have a hemisphere which is having the same height. So for the hemisphere, the height is nothing but the radius, okay? Because this is the center and this is the radius and this is also the radius. So we could have a situation like this, yeah, where I've shown that the bases are overlapping, height is overlapping, correct? Yeah. Or we could have a situation like this, where this is my cone, yeah, and my hemisphere could be like this, where the bases are not overlapping. All right. Yeah. But in this situation, there could be a possibility that the cone's volume could be equal to the hemisphere's volume, right? But in this situation, clearly, when the bases and the, you know, when the bases are overlapping and the height is the same, right? In both the situations, the height is the same. Out here, I've shown that height is the same, correct? Yeah. But the volumes could be different. Yes. So it's a yes no situation from statement B. Okay. Now, taking both statements together, we get only this particular case. Taking both statements together, we get this particular case. That is, the bases are the same. Let me redraw it for you. And the height is the same. Something like this. Yeah. So let me use a different color for the cone. So let's say this is my cone. Yeah. Having the same circular base as the hemisphere. The hemisphere is black in color and the same height, correct? So if this is a situation, then definitely we know that the volume of the hemisphere is not the same as the volume of the cone, because there is this blue color region which the cone is not able to cover, right? And that's the extra portion in the hemisphere, all right? So again, you'll have to go into three-dimensional and imagine these things, right? If you are not able to imagine, then you'll find my explanations difficult. So taking both statements together, I know for a fact that um, you know that we get a definite answer. No. Does a right circular cone have the same volume as hemisphere? So when we take both statements together, no, it does not have. We have a definite no as the answer. So C is the answer for the eighth one. Okay. Right. Moving on to the ninth one. What is the volume of the given cylinder? Right. First statement. So we know that the cylinder has a dimension of 14 centimeters at the diameter. We don't know about the height. Height we don't know. Yeah. So in order to know the volume of the cylinder, remember the cylinder has a volume base area into height. That's the volume of the cylinder. Pi r square, base area of the circular base area, pi r square into the height. Now, when the cylinder is placed inside a rectangular box, the difference between their volumes is equal to 42 times the height of the cylinder, right? So, knowing that the radius is 7 centimeters, yeah, this pi r square is 22 by 7 into 49h. So that 7 goes in 49 7 times. We'll have it 22 times 7, which is 154h. So the cylinder that we have has a volume of 154h. This is without the first statement. Now, when we take the first statement into consideration, then we know that the volume of the box, rectangular box, is 42 times h plus 154h. So we know that the volume of the box is 196h, right? But that doesn't tell us the volume of the given cylinder. So the first statement doesn't give us any information other than the fact that when this cylinder is placed inside a rectangular box, yeah, the difference between their volumes, correct, is 42 times the height of the cylinder. So in terms of h, I got to know that the box is 196h, the volume, and the volume of the cylinder is 154h, right? So yeah, first statement just tells us that the volume of the box is 196h, but again, we don't know the h and we don't get the answer. So A doesn't answer. Second statement on its own. Remember, now we are looking at the second statement. Now from the without the first statement, we have this as the information. We know the volume of the cylinder in terms of height is 154h. So using that and second statement, we'll see if we can get to the answer. If the given cylinder's height is reduced by 30%, it would fit in a box whose height, width, and length would all be equal to the height of the cylinder. So most of you will think it this way that, okay, it's a box, yeah, and clearly this is 14, this is 14, and the height is 14. Yes, because it will be equal to the height of the cylinder. And you're imagining this, right? But that's a wrong imagination. Okay, that's a wrong imagination. So why this is a wrong imagination? Okay, because I can have a bigger box, a cubical box, right? So imagine the height is 40 centimeters. If I reduce by 30%, then it is 12 less. So I get 28 centimeters, right? And that 28 centimeters could be the height, length, width of this particular box. But yet my cylinder would be having a 14 centimeter, yeah, and my length would be the same as the height would be the same as the height of the cubical box. So from the second statement, it could be this situation. If this is a situation, the height is equal to 20 centimeters. Now, if this is a situation, the height is 40 centimeters. Are you with me? Right? So the second statement also doesn't give us a definite answer. We can't find out the volume of the cylinder, right? Height could be 20. It satisfies the second statement. Height could be 40. It satisfies the second statement. Are you with me? It doesn't tell us the height of the cylinder, correct? Yeah. So B is out. Now taking both statements together. When we take both statements together, right, it tells us that the rectangular box has a volume of 196 H. And it could be, second statement tells us it could be any of these two, right? And the second statement is talking about a cubical box, right? Right? It would fit in a box whose height, width, and length would all be equal to the height of the cylinder. All right. So when height, width, and length are equal, then they're talking about a cubical box. And the first one is talking about a rectangular box. But we are not here to discuss the volume of the box. We're here to discuss the volume of the given cylinder. So taking both statements together, we don't get an answer. Yeah, we don't get an answer. Okay, right. Okay. Um, yeah. Yeah. Hmm. So it had the second statements framed in a manner that it was talking about the same rectangular box which becomes a cubical box, right? Then perhaps there could be something to solve for. Then perhaps we could say it is this situation out here, this one out here, okay? Because we know that 14 and 14, yeah, is 196, and then the height. So we could probably say that this is a situation. Had they framed the question in a way that this rectangular box would become like this. Are you with me? But anyway, too many interpretations. So C is also not answering. E is the answer. Ninth one, you don't get an answer. So why these questions are difficult is because um, it's really making you imagine things. Yeah, the numbers are such that it could mean this also, it could mean that also, like the drawings which I've shown you. And so it gets very confusing. Yeah. Okay, last question. Question 10. A rectangular garden with a length of 20 yards can fit how many cubical flower pots end to end? Yeah. So this rectangular garden, we don't know about the width. All we know is that it has a length of 20 yards. Yeah. So we don't know about the width. Okay. First statement, a total of 100 cubical flower pots can fit end to end in a square garden with side length of 40 yards. So obviously we're talking about the same cubical flower pots out here, yeah, as discussed in the main question. So the first statement, a total of 100 cubical flower pots can fit end to end in a square garden with a side length of 40 yards. So the side length 40 yards is its base area is 14 to 40, 1600 square yards. Divide that by 100, yeah, and that gives me the base area of 1 cubical flower pot base area, right? So that's the base area, 16. Are you with me? But then we don't know the width. All we know from the given question is that the cubical flower pot has a square base area of 16 centimeters square. Okay. Or 16 square yards, sorry. 16 square yards. But we don't know about knowing the base area of the cubical flower pot. We don't know about the garden's width. So first statement doesn't answer the question. A's out, D's out. The width in yards of the rectangular garden is equal to the number of square yards found in the square base of the cubical flower pot. All right. So this is all words, no numbers out here discussed whatsoever. So second statement doesn't answer the question. We need to know the width, correct? Yeah. And we need to know the dimension of the cubical flower pot. So we don't know that. But when we take both statements together, we get an answer. How? So taking both statements together, we know that the cubical flower pot has a base area of 16. Yeah, correct. And we also know that the width in yards of the rectangular garden is equal to the number of square yards found in the square base. So we know that this is the same thing as 16 yards. All right. So now I know that I have a garden with 20 yards by 16 yards. And how many of these 16 square yards would fit in, right? How many of the 16 square yards would fit in? So out here, and the base area is 16 square yards. We are talking about 4 by 4 dimension, right? This is 16 square base. So there will be, 4 20 by 4. So there will be 5 of them out here. Like this, there will be 5 of them. And like this, there will be 4 of them. So we know there will be um, 20 total cubical flower pots that could fit into this garden. Yeah, with dimensions 20 by 16. So together it gives us the answer. Anyway, that's it. Thank you very much. Remember, there'll be only 4 more worksheets after this. The topics I had written down somewhere. Hang on. Yeah. The topics are sequence and series, word problems, speed, distance, time, work rate time, and data interpretation and logic. So maybe I need to cover 5 more videos. Thank you.